All right, now that we've discussed Taylor series and the Lagrange remainder, what I want to do now is kind of reconcile everything we've done and compile it just before we start discussing some of the more nuanced aspects of Taylor series, before we start applying it, before we start manipulating it. So what we're going to do today is we're just going to slow down a little bit, and we're going to recap all of the different Taylor series that we know of. Some of these we haven't derived specifically, but we'll discuss how we would derive them in any other case. Okay, let's get started. So, common Taylor series. So we're just going to go through all of them. The first one that you should know is the power series that we discussed earlier. So if we want to have this function, 1 over 1 minus x, we can write that as equivalent to the sum from n equals 0 to infinity of x to the n. So this is just the sum of all the powers. So we've got 1 plus x squared plus x cubed, and all the way on. But, as we know, this is not valid for everywhere. We need to remember our radius of convergence, which is 1. So we can approximate this function with this series when our radius of convergence is equal to 1. So when we are between -1 and 1, we can use this Taylor approximation. Okay. And if we remember, we can generate a lot of different rational functions like this just by molding different functions into this and then making substitutions into that. Okay, so now we move actually onto the functional stuff. So we've got e to the x. Remember, e to the x, that was one of the first ones we determined. So we determined that to find e to the x, we can set that equal to the sum from n equals 0 to infinity of x to the n over n factorial. So this gives us 1 plus x squared over 2 factorial plus x cubed over 3 factorial. We keep going all the way out. And what's nice is that our radius of convergence here is infinite. And so, as you can remember, or as you can probably imagine, what we want to do, if we want to generate a function that's similar to e to the x, like a transformation, just make substitutions like we did in there. Like we did in the power series, the general power series, we can do that with our Taylor series as well. And that will give us any any exponential function that we like. That's e to the x or so. Okay, now we also have sine of x. So, if I want to approximate sine of x, we discussed this earlier, we can make a Maclaurin series. It says from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1 factorial, right? And we can write that again as just its series form, which is x minus x cubed over 3 factorial plus x fifth over 5th factorial minus x 7th over 7 factorial, on and on and on. The radius of convergence for this as well is infinite. I really like the Desmos workshop for this one because you can kind of see how the Taylor approximation works. It just generates all these elementary polynomials that we discussed back in, or that we would have discussed back in like pre-calc or college algebra, and it makes a really nice system that we have. Just keeps going out and making the sine wave. And now, we haven't discussed this explicitly, and we'll discuss it in future videos, but if we wanted to find the Taylor series for cosine, we already know the Taylor series for sine, so it's actually not worth our time, really, to go through finding all the derivatives of cosine using the Lagrange formula to find everything, because a couple videos ago, we discussed how to take derivatives of power series and Taylor series. So you can just take the derivative of this, and then we will get cosine, because the derivative of sine is cosine. And we remember that's a very easy task, because we just get x to the 2n, right? So, here what we get is we get that the cosine is equal to the sum from n equals 0 to infinity of -1 to the n, x to the 2n over 2n factorial. Okay, so this is just the even powers. So for sine, we get all the odd powers. For cosine, we get all the even powers. So that's pretty interesting, I would say. So that is for cosine, and then again, our radius of convergence is infinite. So we can generate sine and cosine waves with these formulae. All right, so now we've got a couple more. I want to discuss the arctangent function. We haven't derived this one explicitly just yet. But to do this, we get the sum from n equals 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1. The only difference between this and the arcsine, or this and the sine function, is that this is not factorial on the bottom. So we get x minus x cubed over 3 plus x fifth over 7 minus x 7th over 7 plus dot, 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 dot. We keep on going. For this, we get a radius of convergence of 1, so that's important. We don't get the full arctan function. Okay, and finally, I would discuss the natural logarithm of 1 plus x. Of course, we can find this because this would be we could find this by integrating the power series function to get that. So for this, I get the sum from n equals 1 to infinity of negative 1 to the n minus 1 times x to the n over n. So what we get here is we get something nice looking. We get x minus x squared over 2 plus x cubed over 3 minus x fourth over 4. No factorial there. And then again, keep going, dot, 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 dot. Radius of convergence here is also 1. So I think it's really important to discuss what we have just done here. We have generated Taylor series for almost every function we can think about. We have one for a logarithm, and we can always maneuver this so that this matches the function that we want to generate. We also have determined a way to model the trig functions. So we've made ones for sine and cosine. Of course, with sine and cosine, all you need to do is write all the other four in terms of sine and cosine. Likewise with tangent, you can express arctangent as arcsine over arccosine. So anyways, what we can do is we can now use this as a toolkit to expand upon our knowledge of Taylor series and really expand upon our knowledge of applications to Taylor series, which is what we're going to do in the next video. We're going to talk about manipulation of Taylor series. Then we're going to talk about applications of Taylor series. Then we're going to be done with Unit 9. Thanks for watching. We'll see you in the next one. Bye.